Hi, my name is Alireza, and I'll present a work done at Columbia University called Weakly Supervised Visual Semantic Parsing. This work is based on the task of scene graph generation, which takes an image and extracts objects and their pairwise interactions. This means finding each object, classifying it, localizing it using a bounding box, and then classifying each pair of objects into a predicate class. The resulting scene graph is a rich representation of the image that has applications in image captioning, image retrieval, image synthesis, and visual question answering. But existing methods for scene graph generation have limitations. They require bounding box supervision for training, which is expensive. Their computational complexity is quadratic as they process every pair of object proposals. And they are limited to pairwise predicates, like a girl eating cake. They cannot express higher order interactions like a girl eating cake with a fork. So to address these limitations, we propose Visual Semantic Parsing, or VSP, which kind of generalizes the scene graph generation task. In VSP, predicates are represented as nodes rather than edges, and edges represent semantic roles that entities play in each predicate. For example, the girl is the subject of eating, and the cake is the object of eating, and we can have the fork as the instrument of eating. So we can have a flexible number of entities interacting with each predicate, which is not possible with scene graphs. Now, to extract this new kind of semantic graph from an image, we propose VSPNet, which is a neural net with sub-quadratic complexity. We also propose how to train VSPNet, especially in weakly supervised settings where ground truth bound boxes are not available. So let's see how VSPNet works. Given an image, we extract region proposals and their features to initialize a set of entity nodes. We also initialize a fixed number of predicate nodes to establish a bipartite graph. Then we compute edges in this graph using what we call role-driven attention. This means for every semantic role, we compute a cross-attention matrix from predicates to entities, and we treat it as an adjacency matrix. We do this for every semantic role, resulting in different types of edge for this graph. Now that we have edges, we propagate context using message passing. But in order to efficiently navigate messages in this complex graph with various types of edge, we propose a mechanism called three-stage message aggregation. This means we first extract outgoing messages for all entities, then we fuse them for every type of edge, then we fuse them again to compute a single incoming message to each predicate. We update the state of each predicate using its incoming message and do the same process in the reverse direction to update entities. After updating all the nodes, we compute the role-driven attention again to update edges, and then we pass messages again to update nodes, and we repeat for a fixed number of times and use the final state to classify entities, predicates, and semantic roles. This concludes the inference process of VSPNet. Now, the next question is how to train it. In training, each image comes with a ground truth semantic graph, but in weakly supervised setting, bounding boxes are not provided for entities. This creates an alignment problem, where we don't know what nodes in the ground truth graph correspond to what nodes in the output graph. The problem is, our objective function depends on this alignment. If we know the corresponding ground truth for each node, we can easily define a classification loss for entities, predicates, and semantic roles. But because we don't know this alignment, we have to define a nested optimization problem. We not only want to find the best model parameters, but also the best alignment for each graph. The first optimization can be typically done using gradients descent, but the second one is a difficult and new optimization problem, and we propose a graph alignment algorithm that can solve it efficiently. Given the current state of the network, we find the best alignment, and we use that to update the network, and we iterate until convergence. So let's see some experiment results. On the visual genome dataset, we show that VSPNet can outperform all weakly supervised baselines. We also provide evaluation experiments that show each component that we proposed are effective. Then we propose an extension of our method to supervised settings, which can utilize ground truth bounding boxes to outperform supervised baselines. Besides being the most accurate, we also show that VSPNet is faster than any existing method, thanks to the bipartite architecture that breaks the quadratic complexity. But most importantly, we show that VSPNet can extract structures that are beyond the capability of existing methods. We can extract things like a person cutting a cake with a knife, or a person holding a tennis racket, or simply a person smiling. This system is open source and available to everyone. Thank you.